How's it going, ladies and gentlemen? Mr. John here again, taking a look at 16.1 and 2 information acids and bases and bronsted-lowry acids and bases. So objectives are as follows. We are going to describe the Arrhenius definition of acids and bases. We're going to describe acids and bases and their reactions in terms of proton transfers. We're going to identify acids and bases and their conjugate acids and bases. Describe what it means to be a strong or weak acid or base, as well as the corresponding strengths of their conjugate base and acids. All right, so the Arrhenius definition is probably one that you are familiar with from like high school chemistry. Acids give off an H plus ion and bases give off an OH minus ion. So it looks like this, right? So this would be our acid because it gave off an H plus ion. And this would be our base because it is giving off an OH minus ion, which makes it our base. All right, so Arrhenius reactions, if we have an acid over here and we have a base, what always happens is it will react to give us water and a salt. So what happens is the acid dissociates, gives you the H plus ion and the Cl minus ion here. And the base is going to dissociate, giving you a positive ion and an OH minus ion, which is going to combine with the H plus to give us water. So we have an acid plus a base always gives us water and a salt. So in solution, the salt will probably ionize and break apart into just Na plus and separate Cl minus ions, but I didn't write it that way for you. All right, bronsted-lowry acids and bases are a little bit different. So, looking at some chemical reactions, and Bronsted-Lowry, saw a pattern. Said, hey, there are things that are acting like acids and bases, but they're not giving us OH minus ions. We're not getting this, but it's still doing the same kind of thing as acids and bases that we've been talking about, right? So, an acid is going to be a proton donor, and a proton is the same thing as an H plus ion, right? Because really, an H is just one proton and one electron, and if you get rid of that electron, you're left with just a proton. So a proton and H plus are the same thing. All right, and a base will be a proton acceptor. It doesn't need to be OH minus. It can be anything as long as it's accepting a proton. So here we go again. This still doing the same thing, giving off a proton, makes it the acid. But now this is going to accept this hydrogen, which is going to make it our base. So NH3 is our base because it accepts a proton. All right, so conjugate acid-base pairs. So right now, I have NH3, which is going to be my base, and I have HCl, which is going to be my acid. But what happens is we have a proton transfer. So conjugate acid-base pairs, the only difference between the two, the acid-base pair, is whether or not there is a proton. So what happens is a proton gets transferred here. So now this NH4 is going to be my conjugate. Oh, there should be an NH there. Whoops. This is going to be my conjugate acid, and NH3 is my base, whereas HCl was my acid, and it becomes my conjugate base over there. So these two are linked because the only difference is whether or not a proton is there, and then these two are linked as well for the same reason. All right, so the only difference is the proton, right? We got NH4 here, NH4 plus, and NH3 over here, so they are conjugates. The only difference is a proton. And we have Cl minus and HCl here. Only difference is a proton. They are conjugates. So here's the chemical equation example, right? So what's happening here? Well, it looks like this H is being transferred to the H2O to give me H3O plus and chloride ion. So what that tells me is that the HCl and the Cl minus are conjugate pairs, and the H2O and the H3O plus are conjugate pairs. So the HCl is acting as the acid because it's giving off a proton, and the chloride ion is my conjugate base. If I looked at it going backwards, right to left, it looks like the chloride ion is acting as a base and taking an H and becoming protonated. So the chloride ion is the conjugate base. Now for water, it looks like water accepts a proton in this reaction. So that makes the water a base and the H3O plus the conjugate acid. Because if we looked in the reverse reaction, it looks like H3O plus would be acting as an acid. It's giving off a proton. So that makes it the conjugate acid. All right, so let's take a look at another one. Now HF and NH3, all right, becoming NH4 plus and F minus. So it looks like these two are linked together because the only difference is the proton, and these two are together. So they're conjugate pairs. Well, HF, let's see, HF gave away a proton, that makes it the acid, which means this fluoride ion is the conjugate base. And NH3 is accepting a proton, which makes it the base, so NH4 will be its conjugate acid. Right, so if I look at the reaction going right to left, fluoride ion is acting like a base, which is why it's the conjugate base, and the ammonium ion is acting like an acid, which makes it the conjugate acid. All right, strong acids and bases. These things will dissociate and completely transfer the protons to water molecules. So what's going to happen is all of the HCl's are going to lose the H and give the H2 and H2O, making it H3O plus. So it's going to look like this. And this is going to be a complete transfer. All the HCl's are going to do that. That's what makes it a strong acid. Bases will do the same thing, except with hydroxide ions or accepting H pluses. All right, so weak acids and weak bases. Here I got HF, which is a weak acid. It is not going to completely dissociate. It's only going to partly dissociate. So if I got all of these HFs, not all of them are going to break apart. Only a couple of them maybe will. And that's what makes it a weak acid. Not all the molecules will break apart and dissociate. All right, so let's take a look at weak acids and bases and their conjugates. All right, so here I got water, HF, becoming H3O plus and fluoride ion. Oops. So HF is a weak acid, which means its conjugate base is going to be a stronger base. And you can think of it this way. It's a weak acid because the H likes hanging out with the fluoride ion. It likes being together. That's why they don't break up completely, only partially. So if I'm looking at the fluoride ion, it wants to take up more H pluses and become hydrogen fluoride. So it's a stronger base than the acid is strong. All right, then we have negligibly acidic things. Basically, hydrogen is present but has no acidic behavior in water. So example would be CH4. It has protons, but it doesn't break up. So this would be negligible or negligibly. I can't spell negligible. But what that means for something like this, if you had the CH3 minus ion, well, this is negligibly acidic because it really likes holding on to these hydrogens. It doesn't want to let them go. So if we had something like this where there was a missing hydrogen, this is going to be a very strong base because if a hydrogen comes along, it's going to hold on to it and bond with it. All right, so conjugates are strong bases. All right, Lewis acids and bases is probably a new one for you guys. You know, Bronsted-Lowry was like, hey, you know, it doesn't have to be an OH minus to act like a base. Lewis even took it a step further. It was like, hey, we don't even need protons to be transferred. So Lewis acids are electron pair acceptors, and Lewis bases are electron pair donators. So if we take a look, it's going to be a more general definition that can be applied when there isn't a proton transfer. So the classic example would be ammonia, which is NH3, and boron trifluoride, or BH3. So ammonia has these unshared electrons that are hanging out over there, and boron is going to be a slightly positive thing going on over there. So they're going to be attracted, right? Boron can bond using those electrons, and we get an acid-base reaction that isn't a transfer of protons. So, to generalize, Arrhenius acids, H plus is given off, base, OH minus is given off. Bronsted-Lowry, you have a proton donor being the acid and a proton acceptor being the base. For Lewis definition, we're not looking at protons or H's, we're looking at electrons. So an acid is an electron pair acceptor, and base is an electron pair donor. So here's a potential point of confusion, because for bronsted-lowry definition, it's protons being donated as the acid, but for the Lewis, it's the bases that are donating an electron pair. So just know that like the acceptor and donation kind of flips when you go from bronsted-lowry to Lewis. Lewis has to do with electrons. It's not a great way to remember it, but I think I think of electrons for the Lewis one. So Lewis is more general, which is why I have this nice graphic. So Arrhenius is the most specific. Then bronsted-lowry will include all Arrhenius acids and bases. So if it's an Arrhenius acid or base, it's also bronsted-lowry acid or base. And Lewis is the most general of them all. If it's a bronsted-lowry, it's also Lewis acid and base. Right. So let's take a look. Which kind of acid-base thing do we got here? We have HCl and NaOH reacting to give us water and salt. So it's going to look like this. So we have H plus given off and an OH minus given off as well. So it's definitely going to be an Arrhenius acid or base, which also means it's also bronsted-lowry and a Lewis acid base. All right, here we had HCl giving off an H plus, right? So it's giving off a proton, and we have NH3 accepting it. So we don't have OH, so it can't be an Arrhenius one. It's going to be the bronsted-lowry definition, right? We have an H plus donor, which was this thing, that was the donor. We have an H plus acceptor, so it's going to be the bronsted-lowry, which also means it's also a Lewis acid-base reaction. And then here we have boron being attracted to the electrons on the ammonia. So let's see, we don't have H plus or OH minus, we don't have protons, we have an electron pair acceptor and electron pair donor. So it's got to be the Lewis definition of acid base right there. So now the question is, can we look at a chemical reaction and determine if things are being a Lewis, bronsted-lowry, or Arrhenius acid base? So we take a look at this one. We got NH3 and BF3, and they react to make one compound. So I don't see OH minus, so I can definitely rule out the Arrhenius definition. There's no protons being transferred, so I can rule out the bronsted-lowry definition, which means that it's got to be the Lewis acid-base definition. All right, next one. We got NH3 and H2O giving me NH4 plus and OH minus. So I have, if I'm looking at this, it looks like I take one of these H's and I give it to the NH3. So I have a proton transfer without OH minus being in my reactants. So proton transfer tells me that it's going to be a bronsted-lowry acid-base reaction. All right. And the last one that I'm going to look at, I have H2SO4 and 2NaOH giving me 2 waters and sodium sulfate. So right here I have OH and I have H pluses, and they're giving me water and a salt. So I got an acid and a base giving me water and a salt. That's definitely the Arrhenius definition. All right, hope you found that helpful, and I'll see you in class. Bring questions.